Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Raissa Estrela with us today. Hi, Raissa.
Hello, Frank. Nice to meet you.
Pleasure.
Thanks for the invitation to be here.
Well, thank you so much for being willing to talk about your really lovely article. I think it's a very nice one. So thanks. Raissa, where are you located at?
I'm in Pasadena, California right now.
Let's see, it is October 20th, 2021 as we're recording this. And usually October is when California gets its best weather, I think anyway. So how is the weather there in Pasadena today?
Yeah, it's getting very cold for me, at least. I'm from Brazil, so I'm very used to warm weather, very tropical. So for me, that's kind of cold. I'm trying to get used to this weather.
Well, here in the Southwest, it's going to be a toasty 30-odd C today. We'll probably hit up into the 90s today. It's cooling off in the morning. It's cooler in the morning, but we're still warming up pretty good. So maybe that's a little bit more familiar with your Brazilian background there. So what is your position there at JPL?
So I am a NASA postdoctoral fellow at JPL.
Cool.
Previously, I was an intern at JPL as well, but I changed it to a NASA postdoc fellow last year.
Okay, cool. So you grew up in Brazil. When did you come to the States?
Yes, I grew up in Brazil and I came to the States in 2018, September 2018, around this time.
Very cool. Very nice. Let's see. Raissa, what do you like to do for research?
Well, I study exoplanets' atmospheres. I also like to study about habitability on exoplanets. So I also been working with impacts of stellar activity on habitability of exoplanets. So I do both, try to detect atmosphere and also try to see any impacts that the stellar side could have into the habitability of planets.
Very nice. That's a nice combo. And that is going to bring us to this very lovely AJ article, Detection of Aerosols at Microbar Pressures in Exoplanet Atmosphere. And Raissa, take us away.
Yes. So this article was motivated especially because haze, aerosols, they are very common in our solar system. We see aerosols in gaseous planets like Saturn and Jupiter, which are aerosols formed by photochemistry due to the UV radiation from the sun that heats the atmosphere of these planets. We also see aerosols, as we call haze, even in small objects in the solar system like Pluto. Pluto has a multi-layer of haze, which is very beautiful, and it was recently we had this beautiful image taken by the New Horizons missions where you can see this extension of the haze in Pluto. And there is even Titan, which is extremely hazy atmosphere, and there it's organic haze, so haze that are formed also due to the photochemistry, UV radiation that comes from the sun, together also with energetic particles that come from Saturn and interact with the atmosphere of Titan, and they form this organic haze that could even be building blocks maybe for life one day. So motivated by this presence of haze that we see so common here in our solar system, we look into exoplanets and we try to find the same. And what we see is that exoplanets also seems to have haze. And there are many observations of exoplanets' atmospheres where you see a slope towards the blue wavelengths that is tried to be explained by Rayleigh scattering in the atmosphere of these planets due to the presence of aerosols in the upper layers. And these aerosols in the upper layers, they could also be blocking information from the near-infrared portion of the spectra, so we would not see water if we expected to see water in these planets, because the upper layer has these aerosols blocking information, blocking the light to pass. So it's very interesting to characterize haze in these planets because of that. One, it's so common in the solar system, and also they could also be preventing us to see information in the exoplanets. And also recently we had a very interesting study of a small terrestrial planet exoplanet, the J1132b, that we also see aerosols in these small planets. So it's not only the gaseous exoplanets, it's also in the small planets. And this could be used as aerosols could be used to detect atmospheres as well in these small planets. So it's pretty interesting.
Cool, nice.
So we took advantage of Hubble in order to understand more about haze in exoplanets. So what we do is we use an instrument on Hubble called STEES, and the STEES has two filters. If you go to figure 1, you're gonna see that there is 2 spectra. Yes, one is a G430L, which is the green spectra that you see here. The other filter is the G750L. So these 2 filters, as you can see in this figure, they are complementary to each other, and they cover from 0.3 up to 1 micron. So they cover most of the visible, where you can characterize haze, and they even get part of the beginning of the near infrared as well. So we implemented these in our pipeline, our JPL pipeline, Excalibur. So Excalibur was built in order to provide a uniform analysis for multiple planets in the same way. So we perform all the data extraction steps in the same manner for all planets. So this allows us to perform comparative planetology of exoplanets. So it's pretty important now, especially for this field of exoplanets atmosphere. So we implemented the STEES, and we performed all the steps, data calibration, obtaining the white light curve, and also the spectral light curve, and finally the transmission spectra of these planets. And once we have the transmission spectra, we can also interpret this spectra using atmospheric retrieval package. So I'm going to show you the transmission spectra. I think it's in the next, one of the next figures.
About figure 2.
Let me see. You
Like
can go downwards. Next page.
next one, okay. Yep, there's your white, and there you go.
It's just, you can stop here. Yeah, so this is the broadband light curve that we obtain, one of the data reduction steps. So the broad white light curve that you see here is for different filters. So you see the STEES G750L in orange. You also see the white light curve for G430L in green, and also the WC3, which is the other Hubble instrument with the filter G141. So here we are combining the effort of these different Hubble instruments. So it's STEES, which observe the visual, plus WFC3 that gives information on the near infrared portion of the spectra. So you can, yes, so you can go move downwards.
Really scattering there. Okay, very good.
So here you see in the figure 4 is the spectral light curves, also one of the last steps in our data reduction, where instead, when we get the spectra of these planets with STEES and WC3, we can sum in each wavelength beam in order to obtain these spectral light curves. So here you see the spectral light curve associated to each wavelength beam, so each different color. So this is going to give the transient depth variation associated to the different colors. This is what gives us the transmission spectra that you're going to see, I believe, in the next figure.
Okay, I'm with you. Good. Okay, let's go to figure 5. There you go.
On the figure 6.
Figure 6.
So figure 6 showed the combined effort of STEES. So the light gray one here is G430L. The dark gray is G750L. So these 2 filters is the ones that I showed in the very beginning, the 2 STEES filters that are complementary to each other. And we also have the WC3 filter that covers the near infrared portion from around 1 to 1.6 micron. So as you can see, when you put everything together, we can get more information about the planet's atmosphere. So in the blue portion with STEES, we see that there is this slope here that seems to give us some hint that there is some aerosols in the atmosphere of the planet. While with the near infrared, with WFC3, we see that there is something around 1.4 microns that could be related to water presence. So we can model these observed spectra here using atmospheric retrieval package, and we have that in our JPL pipeline, which is called Cerberus.
Okay.
So Cerberus gives this light blue solid color that you see in this figure here. So what Cerberus wants to interpret these observations is a haze. So the slope that you see in the model is produced by haze in the atmosphere of the planet that is inducing Rayleigh scattering this blue portion. While at 1.4 microns, see that Cerberus wants some water feature, but this water feature seems to be very small. It's suppressed by the presence of the haze in the upper layer of the atmosphere. And you can see that this haze, this slope, is covering almost 11 scale height of the atmosphere of the planet. So it's extensively distributed in the atmosphere of the planet. So if you go back into the previous figures, figure 5.
Let me ask one question on here. What is delta H here?
Oh, this is the scale height. So this means that 10 delta H is this 10 scale height of the atmosphere of the planet.
I'm with you. Good. Okay, thank you. Figure 5.
So yeah, so just to give more context in the atmospheric retrieval. So in the case of STIS, as I just told you about, we're interested in characterizing the haze. So Cerberus atmospheric retrieval is going to characterize this haze using a Jupiter haze profile. Okay. So we take the Jupiter haze profile that you see here as in the left, in the figure in the left, there is the solid green line. So the solid green line, we can scale it into different properties. So we scale it, we can change the thickness of the Jupiter profile, and you can see this difference in the change of the thickness represented by the dashed lines. And we can also retrieve any information about the location of the peak density of the haze cloud. So you see here, the dashed red line indicates where the peak density is in terms of pressure. So this can be shifted up or down depending on the planet, depending on what the retrieval wants. Okay. And we can also change the optical depth of this haze profile that you can see in the right figure. So yes, we can also scale the optical depth of the haze cloud. So yeah, using this Jupiter haze profile and parameterizing it, Cerberus find that the haze that we want, I think it's in figure 7.
Okay, I'm with you. Figure 7, nice Bayesian corner there. Figure 7, this is figure
7. Figure 8, sorry, figure 8.
All good.
Yes, the figure 8, you see that this parameterized haze profile in red. So this is what our retrieval wants in red, is that the haze in WASP-59b is widely distributed in the atmosphere of the planet. So this haze goes from millibars up to almost microbars. Yeah. So it's covering extensively the atmosphere of the planet. You can see a comparison with the Jupiter haze profile, the one that we use as start base in blue. So you can see how different it is from Jupiter. And this extensive haze profile up to microbar has been predicted in bitheoretical works also before. Other works used photochemistry for other planet, another hot Jupiter planet, and they found that they could also find haze are up to microbars. So our observations here is confirming theoretical predictions of haze at very high altitudes.
Yes, I'm with you.
And so let me see what okay. And then we can also so now we can also try to understand what is the physics behind. So this work is not answering what is the haze, what is the origin of this haze that we see here. Okay. So the observations, we're just detecting the haze, but we are not putting any constraints on what is the physics behind the haze, what is the microphysics, but we can explore some source of opacities that could be that could be associated to this haze that we see in this planet. So one of them is photochemical haze that we also see in our solar system. And photochemical haze, as I said, they were predicted at microbars as well. So this is a possibility. Another possibility could be condensates, silicates, and silicates were predicted, especially for planets that have temperatures above 950 Kelvin.
Okay.
And if you look into figure 7, our retrieval indicates that the atmosphere of this planet has a temperature that's about, I think, 1,400 Kelvin. So here the T in the correlation plot here indicates the temperature that our retrieval finds.
Okay.
So it's around 1,400 Kelvin. So this temperature is very high and is more in agreement with what is expected for condensate by silicates.
Okay.
And also the C2O ratio, which is represented by the TEC1 here in this correlation plot. So the actually, let's go to the table. I think the table is better to see than the correlation plots. So I think it's, let me see.
Where are we at?
I don't remember the number of the table. So
right here.
Oh, this one. Yeah, that big one. Yes. Okay. So here we have, yes, all the parameters that are retrieved by atmospheric retrieval for the atmosphere of this planet. So the C2O ratio that we find, as you can see in the median value, it's very low C2O ratio. So values that are subsolar. So we would expect higher C2O ratios because if it was photochemistry, because photochemistry is induced by the presence of methane. So you would be expecting higher C2O ratio if it was photochemistry. And as I said, temperatures, we would expect lower temperature if it was photochemistry. Higher temperatures are more in agreement with silicates. So these two factors here, temperature and C2O, seems to indicate that these haze are more likely related to condensates than photochemistry.
Okay.
And there is another factor that I'm going to show, I think is one of the last figures in this paper that shows the the UV fluxes. I think is one of the last figures.
Yeah, figure 13.
Yes, so UV fluxes could also give an idea if photochemistry plays a role here into inducing these aerosols. But what we see is that WAS69, which is the blue, one of the blue targets here, medium blue, more or less, compared to all the other targets, the FUV flux of this target is very moderate, so not too high. So we would expect something higher, like for example, WAS19, which is one of the reds with higher FUV flux. This target also have some presence of haze when we look in the spectrum of the planet, but it covers less portion of the atmosphere compared to WAS69b. So we would expect in this case that WAS69b would have higher EUV flux if photochemistry was playing a key role here. But it seems that it's very moderate, it's not too high. So it's another reason that maybe photochemistry is not the main source. So I would say that the next steps for the future would be to look into other planets, look into more planets, and try to have more information about temperature, C2O ratio, and also EUV flux in these other planets in order to make some correlation with the haze that we see in these planets. So we can understand better what is behind, what is the source, what is causing this haze in the atmosphere of the planet. So we need more observations in order to put these observations together with what theory predicts. Right, because theory already gives us a clue of what to expect, but we need more observations in order to see what these planets' observations is saying. Are they really showing the same that the theory is predicting? Yeah. So we need to put these two efforts together: observation plus theory plus more laboratory experiments to constrain temperature, C2O ratios also, and also EUV flux in these planets.
Very cool. Very nice. Raissa, thank you so much for walking us through your very lovely AJ article. And you touched a little bit upon it there in the end. So let me ask one question. What motivated the choice of this particular exoplanet? Was just because you could get good observations of it, or what was sort of the driver of this particular one?
Yeah, these observations were public observations, so it was not our group observation, so they're public available. And when we extract the data, we saw that there was these huge slope and towards the blue. So we said, oh yeah, that should have haze there. We should characterize this haze and see, because it seems that this haze should be covering a bigger portion of the atmosphere of the planet. So once we characterize the haze using our atmospheric retrieval, we see that, yes, it seems that the haze is going up to microbar, so it's going to very lower pressures, as it was already predicted by other groups, theoretical works. So our observations were confirming theoretical predictions. So that's why we thought that would be a cool target to go with.
Absolutely. Very nice. Very nice. And you touched on a little bit about going to the future. So you don't have to spill your next research project if you don't want. But are you going to be looking at other exoplanets that may be in public data, or applying for telescope time yourself to go ahead and pick a target on a couple of exoplanets or something like that?
Yeah, that's the goal of a JPL pipeline, actually, is to perform comparative planetology. So we don't want to just look at one target to understand anything. We want to look for multiple targets and try to perform comparative planetology studies, so we can start to understand what happened this target also happened that one, and the other one or not, or it's only specific for one target, right? So we want to see a sample and try to explain this phenomena, these aerosols phenomena, in a sample, not only these targets specifically.
Very cool. Very nice. I look forward to seeing some of your future papers on this fascinating body of work. It's very cool.
Thank you very much.
So Raissa, thank you again, once again. And that will do, everyone. And I hope this made your astronomy day just a little bit better, and we'll see you on the next one. Bye-bye.